So coming to our molecule, what we find is we get soap. Now this soap, so with increase in tail, the lipophilicity increases, whereas with increase of polar site in molecule, hydrophilicity increases. Alright, so this part I hope is clear. Okay. Let's try and get into understanding micelle. Now we have dirt in our cloth. Now this dirt does not get washed by water. What do? We use soap. Now why do we use soap? Because since the dirt doesn't dissolve in water, so the HLB of dirt is very low, or rather it is oil soluble. So we use surfactant. So now surfactant, and what is surfactant? Surfactant is surface acting agent which has got head and a tail. So now what we have synthesized is soap. So this is the soap that we have synthesized. So what happens is when oil is there in a cloth, then the molecules arrange in a way by which the tail is towards oil part and the head is towards water part. So this is the lipophilic part of surfactant which is holding the oil, that is the dirt, and this is towards the aqueous part, the water. The head is towards water. So as a result of that, what happens is it forms micelle. It is aggregation of surfactant in a particular pattern. Alright. Now suppose it is oil. This entire stuff is oil and there is some water. So you see globules of water, right, in oil. So now if you don't want to see that and want to make emulsion, you would put in this surfactant. What would it do? The head part would hold the aqueous part, the water droplets, and the oil, the lipophilic part would be in oil. So as a result of that, it would form an emulsion. Alright. Whereas here it is used for removing dirt from clothes and many other processes where in a system there are two components. One is oil soluble and one is water soluble. Both are immiscible. So I put this surfactant into it. That would make it homogeneous or would make it emulsion, or that would emulsify. So this is what we call as emulsification. Okay. Surfactants at oil water interface reducing surface tension. So the surfactants are what? Surfactants are those which act at oil at interface. Now in this case it is oil and water interface. In this case it is water and oil interface. So it acts at the interface, reducing surface tension, forming emulsion. So that's the method by which we form emulsion. You are also supposed to know about oil in water, what is oil in water and water in oil type of emulsion. Now if oil in water, we mention it this way, oil in water. So basically you have oil that is dispersed phase and water is dispersion medium. So water which is there, which is the main matrix, that is dispersion medium, and this oil which is there, that is dispersed phase. Alright, now so that is oil in water, where water is main and into it is oil. Now here oil is main and water is in form of droplets. Alright, so here these water droplets are dispersed phase. The oil is dispersion medium. As here it was water which was dispersion medium, here it is oil which is dispersion medium, here it is oil which was dispersed phase, and here it is water which is dispersed phase. Alright, so we have got certain example for this, that is milk, paint and all those things are oil in water. Whereas when we eat butter, cream and all those things, those are water in oil. Alright. Two properties of colloidal dispersion need to be discussed are optical property and kinetic property. In case of optical property, we have heard about Tyndall effect. Now, if we put a torch over here, now this is a clear solution and this is a colloid. Now, when light passes through clear solution, we don't see any light beam in the solution. Whereas in case of emulsion, the light beam is clearly visible. Now this scattering of light, or rather dispersion of light by colloidal particles, makes path of light visible, and this is known as Tyndall cone, and the effect is known as Tyndall effect. Now what are the requirements for that? The diameter of dispersed particles should not be much smaller than wavelength of light focused. Second thing is refractive indices of phase and medium. Dispersed phase and dispersion medium should differ largely. Alright, so these are the two conditions. If conditions follow, we get to see Tyndall cone. The next property that I choose is kinetic property of colloidal dispersion. Now the molecules which are there keeps on moving around, okay, into zigzag motion. Now why does it happen? It all happens because of dispersion medium providing kinetic energy to dispersed molecule. Alright, so collisions of dispersed molecules with fast moving molecules of dispersion medium provide kinetic energy to dispersed molecules, generating endless random zigzag motion named as Brownian motion. Alright, so Tyndall effect and Brownian motion are the properties of colloidal dispersion. Okay, so guys, please keep in mind I have given you some extra knowledge about these things, about emulsification, emulsifier and HLB. Please keep those things in mind because that's going to help you out in solving many numericals. Alright.